Hello, this is Matt Dean with A Plus College Ready, and today we're going to talk about chemical reactions. A chemical reaction is a process during which one or more reactants are changed into products. The reactants are the original substance that existed before the chemical reaction took place. They're normally found on the left-hand side of the arrow, the yield sign. The products are the substance that are produced or made during the chemical reaction. They're normally found on the right-hand side of the yield sign. The law of conservation of matter says that matter is neither created nor destroyed, but can be transformed or transferred. In a chemical equation, and this is not really the first law of thermodynamics, that's for energy. This means that the number of atoms of each element in the equation must be equal on both sides of the reaction arrow. We'll talk about several kinds of reaction equations. Well, we may use word equations where we're only given the names of the reactants and the products. We may have a skeleton equation. This is a chemical equation that has the formulas for the reactants and products written out, but the equation hasn't been balanced yet. Usually we're going to try to work with balanced equations. If we have 2 oxygen atoms on the left side, we also have to have 2 oxygen atoms on the right-hand side of that yield sign. So that's true for a balanced equation. The number of the atoms of each type of element is equal on both sides of that yield sign. We're going to balance the equation using coefficients. Coefficients are whole numbers that we write in front of the formulas of a chemical in an equation to balance out the number of atoms of each type. When you're balancing equations, you can change the coefficients. You can add coefficients, but you don't mess with the subscripts associated with a particular molecule or formula unit. If you change the subscripts, you change the identity of the chemical that you're dealing with. So when we're balancing equations, we're first going to identify the reactants and the products for the reaction. We're going to write out the skeleton equation, which remember is an equation with the formulas of all the chemicals written out. We're then going to count the atoms, and we're going to balance each element one at a time by changing coefficients. And again, don't change the subscripts. You double check once you've done that by recounting the elements on both sides. You make sure that all your coefficients are in the lowest possible ratio. If not, you're going to reduce those coefficients sort of like you would reduce fractions. So here's some examples of balanced equations. We have potassium plus water, so K plus H2O yields potassium hydroxide plus hydrogen gas. Notice that we've got the coefficients of 2, 2, and 2. We had to do that because when we originally wrote out the equation, like so, we had 3 hydrogens over here and only 2 hydrogens over here. So to change that, we had to make a balance. And the easiest way to do that was to put a 2 right here. Well, now that moves the number of hydrogens up to 4. So we can make there be 4 hydrogens over here by placing a 2 in front of the water. So now we have 4 hydrogens. Well, over here we have now 2 potassiums. Over here we only have 1. So we have to put a 2 there to balance that out. And if you check the oxygens, there's 2 oxygens on this side and 2 on this side. Here's another equation. Sodium hydroxide plus sulfuric acid. That yields sodium sulfate plus water. And if you start counting things, to begin with, there's 2 nitrogens, or 2 sodiums rather, on the right, and only 1 on the left. So we put a 2 there to balance that out. Now, the hydrogens aren't balanced. Now we have 4 hydrogens on the left, only 2 on the right. Well, to balance that out, we put a 2 there. That gives us 4 hydrogens. We check to make sure the oxygens are balanced. 2, 6 on this side, 4 here, 2 here, so 6 total. Here's another balanced equation. Again, notice We balance by adding coefficients, the numbers out front. We do not mess with subscripts. If you change these subscripts, you change the identity of the chemical you're dealing with. So we already mentioned some different types of equations. We said that the yield sign looks like this. On the left-hand side of that yield sign, we have the reactants. On the right-hand side, we have the products. There are situations where you might have arrows going both ways, and if that's true, those are called reversible reactions. And that can tell you that the products, once they're formed, can reconvert back into reactants. So we're going to talk about several main kinds of chemical reactions in this class, really 5 of them. And we're going to start first of all with synthesis, or sometimes called direct combination reactions. These are where you're adding 2 elements together to make a compound. We might be in the form of A being one of those elements plus B being the other. Yields a compound, AB. The second type of reaction is decomposition. This is sort of the opposite of a synthesis reaction. This is when you start with a compound and you break it into elements. There are also single replacement reactions. This is typically when a metal replaces another metal from a compound, or it also can be when a halogen replaces another halogen from a compound. And then finally you have a double replacement reaction. These are essentially when 2 metals, typically metals or positive ions, swap places. So you might have these 2 cations, or positive ions, switching partners. So let's first talk about direct combination or synthesis. We talked about the basic equation, looks like this. We're adding together 2 elements to make a compound. There are synthesis reactions with oxygen gas. For example, we see here, we might react magnesium with oxygen to make magnesium oxide. There are also synthesis reactions with sulfur. So you might react magnesium and sulfur to make magnesium sulfide. There are synthesis reactions with group 1 metals and halogens. For example, we might react lithium and chloride together, or chlorine gas rather, to make lithium chloride. You could do the same with the group 2 metal and a halogen, calcium plus chlorine to make calcium chloride. This one's a little tricky. You can react a metallic chloride, for example, like magnesium, a metallic oxide rather, like magnesium oxide plus water, and that yields a metallic hydroxide or a base. Well, the only metal involved in the problem is magnesium, so it has to be magnesium hydroxide, like so. And then the last one is a 9-metal oxide plus water, and those yield what are called oxyacids, or acids. So for example, we might take sulfur dioxide plus water to yield an acid, and that could be H2SO3. We've also got decomposition reactions. There's several types. One is when we take a metallic carbonate and we might heat it, which we might show with a delta side. And metallic carbonates, when heated, break up into metallic oxides plus CO2. For example, if we had calcium carbonate and we heated it, we end up with calcium oxide plus carbon dioxide. We might have a metallic chlorate, for example, potassium chlorate, heated up, will yield a metallic chloride, KCl, plus oxygen gas. And we'd have to balance. This equation is not balanced right now. To do that, it looks like we probably need to put a 2 here, and a 2 here, and a 3 there. You can break up acids to yield a 9-metal oxide plus water. You can break down bases, for example, NaOH. If you heat that up, you can get a metallic oxide plus water. Again, you would need to balance by putting a 2 there. And that's balanced as written. And then some particular, or a metallic oxide can be broken up into a metal plus oxygen gas. For example, let's say you had calcium oxide and you heated it. You might get Ca plus O2, balance with a 2 there and a 2 there. And then there are cases when you can break down some compounds using electricity. For example, maybe you take sodium chloride, this would be like aqueous sodium or liquid sodium chloride molten, and you run electricity through it. You might be able to break it up into sodium and chlorine gas, and you need to balance with a 2 and a 2. So decomposition reactions, you're breaking apart compounds. Single replacement reactions. Before we talk about single replacement reactions, we need to look at what's called the activity series. This essentially ranks metals from most active, up here at lithium, down to less active, platinum rather, and gold. Also, we could think of halogens the same way, something like so, in the order they are in the periodic table, fluorine being the most active, iodine less active. So some rules. Sodium and above, we're talking about above on the activity series, will replace one hydrogen atom from water. For example, we might have sodium plus water. The sodium will replace one of these hydrogens, giving you hydrogen gas because it's diatomic in nature. If you only knock off the one hydrogen from each water, that leaves an OH. So you end up with NaOH. And then you would need to balance that by putting a 2 here, and a 2 here, and a 2 here, like so. But only elements, sodium and above on the activity series, will react with water. If an element is above sodium on the activity series, we would say no reaction. For example, if we had copper plus water, copper is below sodium on the activity series, that is a no reaction. Metals above hydrogen on the activity series replace all the hydrogen from an acid. For example, if we had zinc plus sulfuric acid, the zinc replaces all the hydrogen from the acid to give us zinc sulfate plus hydrogen gas. Also, metals can replace other metals from a compound. For example, we might have zinc plus copper chloride. For this to happen, zinc has to be above copper on the activity series. And as you can see, zinc is above copper. So zinc will replace copper. So we'll end up with zinc chloride plus copper metal. Now on the other hand, if we took copper plus zinc chloride, this would be a no reaction because copper is not more active than zinc and therefore it cannot replace it. The other example of a single replacement reaction that you need to be familiar with are more active halogens can replace less active halogens from a compound. So for example, you might have chlorine gas plus sodium iodide. Chlorine is above iodine in the periodic table and in the activity series of halogens. So it will replace it. So you'll get sodium chloride plus I2. Now on the other hand, if you had chlorine plus sodium fluoride, chlorine is less active than fluorine. It will not replace it, and therefore you will get a no reaction. So the next to last type of reaction we need to mention is called double replacement reactions. There's several things that can happen here. One case, we can have two soluble salts, two aqueous salts reacting together to produce an insoluble salt, a precipitate, plus an insoluble salt. For example, we might have lead nitrate, lead 2 nitrate, plus sodium chloride. These react, they switch partners, the cation switch places. We get sodium nitrate, which if we check our solubility rules is aqueous, and lead 2 chloride, if we check those rules, we find that this is not aqueous. This is a solid. It's going to precipitate. Speaking of solubility rules, first of all, let's balance. Like so, let's look at the solubility rules. So these rules tell us which compounds are going to be aqueous or soluble and which ones are going to form precipitates or be insoluble. So for that last example, all sodium compounds are soluble. All chlorides and most iodides and bromides are soluble except for those of silver, mercury, and lead. So lead chloride is not soluble, it's a precipitate. All right, so then we have ammonium salts plus a base. And those give us some weird compounds. So let's take an ammonium salt. Let's take a NH4F plus a base. Let's just say KOH. They're going to double replace. So we're going to get KF plus, it looks like we should get it NH4OH. But this compound, ammonium hydroxide, is unstable and quickly breaks apart. And instead of being NH4OH, it becomes NH3, which is a gas. You're going to see bubbles, plus water, H2O, which is a liquid in this case. All right. So a similar kind of reaction happens when you react a carbonate with an acid. For example, let's say we had potassium carbonate, and let's say we're reacting that with HCl. So we're going to get potassium chloride, and it looks like we ought to get hydrogen carbonate or carbonic acid. But like the ammonium hydroxide, H2CO3 is unstable. It breaks apart, and it yields H2O plus CO2. H2O being a liquid, CO2 being a gas. So double replacement reactions only happen if we form one of three things. Either an insoluble salt, a precipitate, a liquid like water, or a gas like CO2 or ammonia. Another example of a double replacement reaction is an acid-base reaction or a neutralization reaction. For example, maybe we take NaOH plus HCl. Those double replace. We get NaCl, which is an aqueous salt, a soluble salt, plus water, which is a liquid. Let's look at an example where there wouldn't be a reaction. Let's say that we were reacting together potassium nitrate plus sodium chloride, both aqueous salts. They switch places. We get sodium nitrate, which is also aqueous, plus potassium chloride, which again is aqueous. So what that means is that we're starting off with a bunch of ions floating around in water over here, and once the reaction takes place, or doesn't take place really in this case, we have the same exact ions floating around in the same way. So nothing really changed. So if your double replacement reaction seems to yield two aqueous salts, we're going to say instead that this is a no reaction because nothing really changes.
Oftentimes when working with double replacement reactions, we'll be asked to write out molecular, complete ionic, and net ionic equations. A molecular equation is the equation that you're familiar with. Sometimes it's simply called a balanced equation. In a molecular equation, all the compounds are represented as neutral compounds using their molecular formula. For example, if we reacted sodium chloride and silver nitrate, we would get this molecular formula. And notice that it's balanced as written. Remember that aqueous means that a compound is soluble in water. It'll dissolve. It'll break up into its ions. While S means that the compound is insoluble and it's going to form a solid precipitate in the water. If we form a gas, instead of writing S or AQ, we'll just write a G in parentheses beside the product. So next, if we imagine zooming in on the contents of our beaker that this reaction is taking place in, you're not going to find molecules or formula units of NaCl, AgNO3, or NO3 because these are soluble salts. And when they're put in water, they dissociate into their ions. So sodium chloride is going to be disassociated into Na plus and Cl minus. AgNO3 is going to be disassociated into Ag plus and NO3 minus. Sodium nitrate is going to be Na plus and NO3 minus. On the other hand, AgCl, since it's an insoluble salt, it's going to form a precipitate, solid in the water. We'll be able to see that. So when we're writing a complete ionic equation, we're going to take any compounds that are aqueous and we're going to disassociate those into their ions. And we can see that here. So we broke sodium chloride up into Na plus and Cl minus. We broke silver nitrate up into Ag plus and NO3. There should be a minus right here. We broke sodium nitrate up into Na plus and NO3 minus. Silver nitrate, since it's an insoluble salt, does not get broken up. It doesn't dissociate. So as a general rule, soluble ionic compounds like salts, strong acids, and strong bases should be written as dissociated ions in the complete ionic equation. Insoluble salts like AgCl and also weak acids or bases are usually written as a neutral because even though they might dissociate a little bit, it's to a very small extent. If we take a little closer look at the complete ionic equation, we're going to see that some of the atoms appear exactly the same on both sides of the reaction arrow, the yield sign. And in this particular case, notice there's sodium in the aqueous form here and sodium in the aqueous form here. There's also nitrate in the aqueous form here and over here. Those elements, since they're the same on both sides, are called spectator ions. They don't really participate in the reaction at all. They're floating around in the solution before the reaction. They're still floating around in the container after the reaction. So to get a net ionic equation, we're going to cancel those items out. And what we're left with, in this case, is the chloride ion, the silver ion, and they're going to react together to form the solid silver chloride precipitate. This is our net ionic equation.
The last type of reaction we'll mention are combustion reactions. When we talk about combusting things, we're reacting those things with oxygen. Three products really are usually formed in combustion reactions. Those are CO2, water, and usually heat or some type of energy. So typically the things that we're combusting are usually organic. So for example, here we're reacting propane, C3H8, plus water. Notice our three products are carbon dioxide, gas, water vapor, plus heat and light. So in combustion reactions, a carbon-based chemical, a hydrocarbon, reacts with oxygen gas, and it yields carbon dioxide, water vapor, and heat and light. Or heat or light at least.
Another item that we want to discuss is that reactions are also often categorized as being either endothermic or exothermic. Endothermic reactions absorb energy from their surrounding environment as the reaction takes place. They're taking in energy to help the reaction happen, and oftentimes the container in which this reaction is taking place gets cold. There are actually some reactions that you can actually freeze things around the container that the reaction absorbs so much heat from the environment. On the other hand, exothermic reactions oftentimes release heat to the surroundings as they take place. In this case, the container in which these reactions are taking place often gets hot as the reaction releases energy to the container and to the surroundings.